In our quest to conquer the cosmos, faster than light travel remains an intriguing yet elusive concept. The speed of light, a constant 299,792 kilometers per second, is the universe's speed limit according to Einstein's theory of relativity. It's an imposing wall daunting to our ambitions of interstellar exploration. In this video, we'll delve into 10 theoretical methods that challenge this barrier, exploring concepts from quantum mechanics to exotic matter and even time travel to propose intriguing possibilities of journeying beyond the speed of light. Number 1. Warp drive, bending the fabric of space-time. The concept of a warp drive, famously featured in science fiction franchises like Star Trek, involves bending the very fabric of space-time to achieve faster-than-light FTL speeds. But is it purely science fiction, or does it have roots in science fact? Albert Einstein's theory of general relativity presents the universe not as static but dynamic, where massive objects cause a distortion in space-time, creating what we perceive as gravity. This leads to a tantalizing proposition: if matter can warp space-time, can we engineer this process to serve our purposes? Well, Mexican theoretical physicist Miguel Alcubierre proposed a mathematical model for such a concept in 1994. The Alcubierre drive, as it's now called, suggests the idea of creating a warp bubble. Inside this bubble, a spacecraft remains stationary relative to its immediate surroundings. However, space-time itself is manipulated around the craft. It contracts in front and expands behind. This allows the craft to move from point A to point B faster than light could in normal space, without technically breaking the light speed barrier or violating the laws of physics. The concept works on a principle somewhat analogous to an airport's moving walkway. The walkway, space-time moves while you, the spacecraft, can stand still, yet you traverse the distance more swiftly than by walking. However, the Alcubierre drive does come with some monumental challenges. First, it requires negative energy or exotic matter, a theoretical substance with properties that violate classical conditions of energy. It's not yet confirmed whether such matter even exists. Second, the energy requirements are astronomical, potentially equivalent to the mass energy of a planet or even a star. Moreover, other issues arise, such as potential causality violations, time paradoxes, and immense tidal forces that could destroy destinations before arrival. The spaceship might also be trapped inside the warp bubble, and releasing it could release high-energy particles which might be hazardous. Yet, despite these challenges, research into warp drive technology continues, fueled by the enticing possibility of traversing unimaginable distances in the blink of an eye. Recent developments in quantum physics and studies into dark energy and exotic matter provide a glimmer of hope that one day the warp drive might transition from science fiction to science reality. Number 2. Wormholes, taking shortcuts through space. In the grand cosmic highway, wormholes are theorized to be shortcuts, tunnels connecting distant regions in the universe. If they exist, they could enable interstellar or even intergalactic travel within human lifetimes, circumventing the universal speed limit of light. Wormholes emerge from the equations of general relativity, where the warping of space-time by mass and energy could create a tunnel between 2 points. Imagine a piece of paper representing the fabric of space-time. Normally, traveling from one side to the other would require crossing the entire surface. But if the paper is folded over, bringing 2 points close together, and a hole is made connecting them, you've got a simplified model of a wormhole. In more accurate terms, wormholes involve traversable tunnels through the 4th dimension, connecting at 2 points in 3-dimensional space. From our 3-dimensional perspective, it seems like we've jumped instantly from one place to another, seemingly violating the speed of light. However, within the 4-dimensional space-time, the speed of light hasn't been exceeded. However, there is a huge caveat to this exciting concept: stability. According to general relativity, any naturally occurring wormhole would be extremely unstable, collapsing instantly after formation. keeping a wormhole open would require some form of exotic matter with a negative energy density or negative pressure. We don't yet have definitive proof that such matter exists in our universe. Furthermore, creating a wormhole would potentially require manipulating singularities, points of infinite density at the centers of black holes, and involves the complexities of quantum gravity, a theory that is yet to be fully understood or formulated. And even if we could create and stabilize a wormhole, there's the issue of navigation. Wormholes might not lead where we want to go. They could connect to vastly distant places or times, or to entirely different universes if multiverse theories hold true. And lastly, traversing a wormhole might be risky. Astrophysicist Kip Thorne speculates about feedback, a time-looping version of the infamous amplifier feedback whine only with radiation instead of sound. The first object entering the wormhole might cause an infinite loop of self-energizing radiation that could destroy the wormhole and the object itself. Nevertheless, the concept of wormholes remains an active field of research. They offer fascinating possibilities not only for travel, but also for understanding the universe's fundamental nature, uniting the macroscopic rules of general relativity with the microscopic laws of quantum mechanics. Number 3. Quantum entanglement, instantaneous communication across vast distances. Quantum entanglement, one of the most peculiar phenomena in quantum mechanics, presents an avenue for instantaneous communication, seemingly defying the speed of light barrier. This phenomenon occurs when two or more particles become entangled in such a way that the state of one instantaneously influences the state of the other, no matter the distance separating them. Quantum entanglement was first highlighted by Albert Einstein, Boris Podolsky, and Nathan Rosen in a 1935 paper. Einstein famously referred to it as spooky action at a distance, as it seemed to violate his theory of relativity, which posits that nothing can travel faster than light, not even information. And yet, despite his reservations, quantum entanglement has been empirically verified through tests of Bell's inequalities and is now an established part of quantum theory. One might envision a hypothetical use of entanglement for faster-than-light communication or quantum teleportation. For instance, two parties could share a pair of entangled particles. A change made to the state of one particle would instantly reflect in its entangled partner, providing a medium for transmitting information instantaneously regardless of distance. However, despite its captivating potential, using quantum entanglement for faster-than-light travel or communication encounters some significant obstacles. Firstly, it's important to understand that entanglement doesn't involve the transfer of classical information. The quantum states that are linked do not correspond to readable information until they're measured, and the measurement outcomes appear random. In other words, you can't control the state you're sending and therefore can't transmit meaningful information. Secondly, even if we could control the quantum states, any attempt to measure or manipulate a quantum system generally results in the collapse of the entanglement, a phenomenon known as decoherence. Maintaining stable long-distance entanglement and reliably measuring entangled particles are formidable challenges. And lastly, even if these issues were overcome, the no-communication theorem in quantum mechanics states that it's impossible to transmit classical information via a quantum channel alone. And so, while quantum entanglement opens exciting possibilities for understanding the quantum world's mysterious nature and has practical applications in quantum computing and cryptography, its utility for faster-than-light travel or communication is, with our current understanding, highly unlikely. Number 4. Tachyons, hypothetical faster-than-light particles. Tachyons are hypothetical particles that exist solely in the realm of theoretical physics, yet they captivate our imagination with the potential of faster-than-light travel. The term tachyon is derived from the Greek word tachys, meaning swift. These particles are proposed to travel faster than light and have some quite peculiar properties. The existence of tachyons stems from the principles of special relativity and quantum field theory. Unlike normal particles known as bradyons, which require infinite energy to reach the speed of light, tachyons would require infinite energy to slow down to the speed of light. This is because, in theory, tachyons possess imaginary mass, or more accurately, mass squared that's negative, leading to an imaginary result when square-rooted in the energy-momentum relation. The presence of imaginary mass leads to an inversion of many properties we associate with normal particles. For example, when tachyons lose energy, they speed up and vice versa. They would also experience time in reverse from our perspective. However, the existence of tachyons is fraught with complications and paradoxes, the most significant being causality violations. If tachyons can transmit information faster than light, they could create scenarios where cause and effect are reversed. An event could occur before its cause, creating tachyonic anti-telephone paradoxes. It's also crucial to note, despite decades of searching, we've found no empirical evidence of tachyons. Some phenomena initially attributed to tachyons, such as faster-than-light neutrinos detected by the Opera experiment, were later debunked due to experimental errors. Furthermore, most physicists interpret the appearance of tachyons in a theory as a sign of instability in that theory. In the context of quantum field theory, for instance, a system predicting tachyons will typically decay to a different, stable state that doesn't contain tachyons. Therefore, while the notion of tachyons is intriguing, they remain within the realm of speculation. The consensus among physicists is that faster-than-light particles are unlikely to exist, given our current understanding of the laws of physics. But should future research prove otherwise, it would require profound changes to these foundational principles. Number 5. Alcubierre drive, theoretical propulsion beyond light speed. The Alcubierre drive, a concept proposed by theoretical physicist Miguel Alcubierre, is an exciting proposition within the realm of faster-than-light travel. Named after its originator, this theoretical propulsion system is based on the principles of Einstein's general relativity, promising to overcome the universal speed limit of light. At its core, the Alcubierre drive involves creating a space-time bubble around a spacecraft. The concept leverages the malleable fabric of space-time as described by Einstein's field equations. The drive contracts space-time in front of the spaceship and expands it behind, effectively creating a wave upon which the spaceship surfs. Consequently, the spaceship could reach its destination faster than light, traveling through unwarped space without locally exceeding the speed of light or violating the laws of physics. Importantly, the spaceship and everything within it would remain in free fall during the journey, avoiding the detrimental effects of time dilation and high acceleration. Passengers would perceive the journey as occurring instantaneously or in a very short duration, regardless of the distance traversed. Despite its promise, though, the Alcubierre drive is not without some significant challenges. Primarily, its theoretical operation requires negative energy or exotic matter, a type of matter that has not been empirically confirmed to exist. Exotic matter has properties like negative mass and could violate several energy conditions, raising questions about its compatibility with the known laws of physics. And even if exotic matter exists, the energy required to manipulate space-time as proposed by the Alcubierre drive is tremendous, equivalent to converting the mass of a planet or a star entirely into energy, according to some calculations. Furthermore, recent studies suggest potential complications such as high-energy particle buildup at the bubble's front and the inability to stop or steer the drive once activated. Additionally, the Alcubierre drive's hypothetical operation could result in causality violations, creating time travel paradoxes and raising profound questions about our understanding of reality. It's essential to note that the Alcubierre drive is currently a theoretical construct without any experimental evidence or technological blueprint for realization. However, its very conception has provoked significant interest in the scientific community, inspiring ongoing research in general relativity, quantum field theory, and exotic matter. And so, while we may be far from building a practical warp drive, the journey to unravel its mysteries promises to enrich our understanding of the universe. Number 6. Negative energy, fueling faster than light travel. Negative energy, a concept that seems to defy our everyday understanding of energy, may hold the key to powering faster than light travel concepts such as warp drives and traversable wormholes. This counterintuitive notion arises from the realms of quantum physics and general relativity, suggesting the existence of energy that is, in a sense, less than nothing. In classical physics, the concept of negative energy doesn't exist. Energy is always a positive quantity. However, quantum mechanics and the associated concept of quantum fields allow for regions of negative energy under specific conditions. A well-known example of this is the Casimir effect, where two uncharged metal plates in a vacuum experience an attractive force due to a negative energy density between them. One of the most intriguing applications of negative energy is in the domain of faster-than-light travel. Both warp drives and wormholes, as theoretically proposed, rely on negative energy to function. The Alcubierre warp drive, as mentioned, for instance, relies on negative energy to create a bubble of warped space-time, allowing the spacecraft within to ride a wave of space-time and effectively move faster than light. Similarly, maintaining the stability of a wormhole, a shortcut through space-time, theoretically requires negative energy to prevent its collapse. Despite the intriguing possibilities, though, the use of negative energy for faster-than-light travel is riddled with challenges. Firstly, while quantum mechanics allows for negative energy, it's usually on minute scales and for incredibly brief periods, as per the Heisenberg uncertainty principle. Producing a significant amount of negative energy and maintaining it for a prolonged period seems currently beyond our reach. Secondly, the concept of negative energy raises several concerns about the violation of fundamental energy conditions. It may lead to a host of paradoxical scenarios, including time travel paradoxes and the creation of perpetual motion machines, seemingly violating the second law of thermodynamics. And finally, there's the issue of quantum interest, a theoretical principle suggesting that any attempt to accumulate significant negative energy will lead to massive positive energy pulses, nullifying the negative energy effect. The exploration of negative energy continues to inspire physicists nonetheless. It challenges our understanding of the universe and may potentially revolutionize our approach to space travel and energy production. Number 7. Time travel, beating light by traveling through time. Time travel, a staple of science fiction, offers a unique spin on the concept of faster-than-light travel. Instead of striving to exceed the speed of light physically, time travel proposes to cheat the distance by moving through time. The concept of time travel originates from Einstein's theory of relativity, which revolutionized our understanding of time. In this framework, time is not an absolute universal clock, but rather a dimension interwoven with space to form the four-dimensional fabric of space-time. And gravity, a result of massive bodies warping this fabric, influences not only the path of moving objects, but also the flow of time itself, a phenomenon known as gravitational time dilation. And this effect has been empirically verified through experiments like the Hafele-Keating experiment, where atomic clocks aboard circulating planes showed time discrepancies compared to stationary clocks. These effects, while minute in everyday life, could become significant near massive objects like black holes or wormholes. Now, time travel into the future, in principle, is not contentious. Traveling close to the speed of light or near a massive body could slow time for the traveler, allowing them to leap into the future. However, backward time travel is far more problematic. To achieve this, one would need to create closed time-like curves, CTCs, paths in space-time that loop back on themselves. Now, certain solutions of Einstein's field equations like the Gödel universe and the Kerr black hole do predict the existence of CTCs and thus backward time travel. However, these solutions require very specific and extreme conditions, such as a universe rotating as a whole or black holes with particular properties. Furthermore, backward time travel introduces the possibility of causality violations, leading to paradoxes like the infamous grandfather paradox. Some physicists propose that quantum mechanics might prevent such paradoxes through a mechanism called the Novikov self-consistency principle, but these are highly speculative areas. Most physicists treat the idea of time travel, especially backward time travel, with skepticism. It's generally believed that a yet-to-be-formulated theory of quantum gravity reconciling general relativity with quantum mechanics might prohibit CTCs or resolve time travel paradoxes. The concept of time travel sparks immense fascination. It's not only a subject of scientific inquiry, but also a profound philosophical question, probing the very nature of reality, causality, and the flow of time. Number 8. Exotic matter, the key to propulsion beyond light speed. Exotic matter, a term that encapsulates forms of matter that defy our conventional understanding, holds a special place in theories of faster-than-light travel. The phrase exotic doesn't denote a specific type of matter. Instead, it refers to any kind of matter with properties not seen in the standard matter around us. A recurring theme in faster-than-light travel theories is the need for exotic matter to circumvent the universal speed limit imposed by light. Exotic matter with peculiar properties such as negative mass or negative energy density often crops up in the equations of general relativity. The most well-known examples of exotic matter's potential application lie in the theoretical frameworks of the Alcubierre drive and traversable wormholes. In the Alcubierre drive, a space-time bubble created and sustained by exotic matter allows a spaceship to surf a wave of space-time, effectively moving faster than light. Similarly, for wormholes, exotic matter is required to counteract the natural tendency of these space-time tunnels to collapse, allowing for their potential use as cosmic shortcuts. While exotic matter's existence is mathematically permissible, its physical existence and properties remain subjects of intense debate. As of today, no conclusive experimental evidence has confirmed the existence of exotic matter. Furthermore, exotic matter's potential implications are troubling for theoretical physics. Its existence might violate several energy conditions, leading to theoretical inconsistencies and paradoxical scenarios like time travel and perpetual motion machines. Lastly, even if exotic matter does exist, manipulating it to the scale and precision required for faster-than-light propulsion represents a tremendous technological challenge far beyond our current capabilities. Yet, despite these significant challenges, the exploration of exotic matter offers a valuable route to push the boundaries of our understanding. Its study promises not only potential breakthroughs in propulsion technology, but also profound insights into the nature of the universe, the unification of its fundamental forces, and the interplay of quantum mechanics and general relativity. Number 9. Quantum tunneling, a potential mechanism for superluminal travel. Quantum tunneling, a bizarre yet fundamental aspect of quantum mechanics, introduces another way to circumnavigate the speed of light restriction. It allows particles to pass through barriers seemingly insurmountable according to classical physics, hinting at a mechanism for potential superluminal travel. The concept of quantum tunneling originates from the Heisenberg uncertainty principle, a cornerstone of quantum mechanics. This principle suggests a fundamental limit to the precision with which certain pairs of physical properties of a particle can be simultaneously known. One of these pairs is position and momentum. The consequence of this uncertainty is that particles can be found in regions of space where, classically, they should not exist. This quantum mechanical effect allows particles to tunnel through barriers. A classic example is the alpha decay of a nucleus, wherein the alpha particle, classically trapped within the nucleus due to a high-energy barrier, can still escape via tunneling. In theory, if an object could harness this phenomenon on a macroscopic scale, it could tunnel through space-time barriers, potentially facilitating faster-than-light travel. An object could appear to instantaneously jump from one point in space to another, bypassing the intervening distance and thereby seeming to exceed the speed of light. However, quantum tunneling is laden with significant challenges and unknowns when considering faster-than-light travel. Firstly, the tunneling effect is profoundly different from conventional motion. It's a probabilistic effect, which means it's not something we can control or predict with certainty. For example, an alpha particle doesn't choose when to tunnel out of a nucleus, it's a random event. Secondly, quantum tunneling is predominantly a microscopic phenomenon. While there have been observations of quantum behavior at macroscopic scales, such as superconductivity and Bose-Einstein condensates, extending the tunneling effect to the scale of a spacecraft is currently beyond comprehension. Additionally, even if macroscopic quantum tunneling were possible, causality and time-ordering issues might arise, posing challenges to our understanding of space-time and relativity. Despite these complications, though, the study of quantum tunneling continues to be a vibrant field in quantum mechanics. Its investigation not only deepens our understanding of the quantum world, but also nurtures our imagination about the possibilities of superluminal travel. And so even if its application to faster-than-light travel remains speculative, quantum tunneling undeniably demonstrates the intriguing and often counterintuitive nature of our universe. Number 10. Advanced civilizations and the Kardashev scale, harnessing energy to exceed light speed. When contemplating faster-than-light travel, considering advanced civilizations' potential capabilities offers a profound perspective. The Kardashev scale, a theoretical framework proposed by Russian astrophysicist Nikolai Kardashev, provides a means to gauge a civilization's advancement based on its energy utilization. This scale can be extrapolated to estimate the energy demands for faster-than-light travel, which seem currently unattainable but may be within the grasp of highly advanced civilizations. The Kardashev scale consists of 3 types of civilizations. A Type 1 civilization, often referred to as a planetary civilization, can use and store all the energy available on its planet. In contrast, a Type 2 civilization, or stellar civilization, can harness the total energy output of its star, typically through a hypothetical megastructure known as a Dyson sphere. A Type 3 civilization, a galactic civilization, has the capacity to control and exploit the energy of an entire galaxy. It's important to note that our current civilization doesn't yet qualify as even a Type 1 civilization. Now, the energy requirements for concepts like the Alcubierre drive or maintaining traversable wormholes are astronomically high, often estimated to be on the order of converting the mass of a planet or even a star entirely into energy. Such energy manipulation is currently beyond our means, but for a Type 2 or Type 3 civilization, it might be feasible. Envisaging highly advanced civilizations and their potential mastery over energy helps us appreciate the magnitude of the challenge of faster-than-light travel. It encourages us to think big, to imagine manipulating the very fabric of space-time on a cosmic scale, a task that would likely require energy sources and technologies far beyond our current understanding and capabilities. However, this line of thought also prompts us to consider the Fermi paradox, which asks, if there are advanced civilizations capable of such feats, where are they? Why have we not observed signs of their existence or their faster-than-light travel endeavors? Nevertheless, the Kardashev scale and the notion of advanced civilizations provide a stimulating framework for thinking about faster-than-light travel. While they underline the monumental challenges involved, they also highlight the awe-inspiring potential of technological and scientific progress.